Okay, hi everyone. Can you hear me? I should mute. Good. Okay. Hello, this is Tia Eunbyeol. In this session, we will cover CNN implementation using the PyTorch library. In the part one, we will first build a simple CNN for classifying the MNIST dataset. And in the second part, we will implement ResNet, residual neural network, and train it on Cypher10 dataset to demonstrate the effectiveness of residual connections. Yeah, actually, I can see the message. If you have any questions, yeah, just give me a question, okay. We will start by importing the required libraries and dataset. So let's run this code. Yeah, first let's import the necessary libraries that we will use throughout this practice. We'll use a torch and torch vision to load and process the dataset. Yeah, it took a while. Okay. And then run this code. We will begin by setting up the MNIST dataset. First, define the train and test dataset using a torch vision.dataset.mnist. And then split the train dataset into train and validation set like this. Since there's no validation, and then apply the data loader for each set like this. Please note that we will shuffle the training and validation data set. Yeah, shuffle equals true, but yeah, not shuffle the test set. Yeah, not for the test and validation set. Okay. The next, we're gonna use Cypher10 in the second part, so let's import the Cypher10. Cypher10 dataset contains 60,000 3230 color image in 10 classes. I hope these all dataset would be familiar with you guys. And yeah, we're gonna normalize the image using the mean and standard deviation values for the red, green, and blue channel, respectively. Yeah, red for red mean and standard deviation, and blue, green. Okay. This ensures that each channel has a mean of 0 and a standard deviation of 1. And yeah, there's some argument like random crop or random horizontal. We will apply image transformation such as random crop or horizontal flip to augment the training data. Yeah, this helps the model generalize better. Okay. Yeah, of course, for the test data set, we don't need to apply transformation like random crop or horizontal flip. Okay, now let's move on defining the component of CNN. Sorry, but Yeah, as you know, convolution layers are the core building blocks of CNN. In PyTorch, we can define this layer. We can easily define this layer using torch.nn.conv2d. When creating a convolution layer, we need to specify several parameters like input channels, output channels, corner size, stride, and padding. You can easily search the document, PyTorch document for conv2d. Yeah, as you can see, stride and padding have default value, but we should specify input channel, output channel, and corner size. Okay, let's practice. Here's a random tensor, x with a shape of 1 by 3 by 32 by 32, where 1 represents the batch size. It means one image, just one image, and 3 represent RGB channel, and 32 by 32 is the spatial size of the image. Your goal is to pass this tensor through some convolution layer and make the output size 1 by 1 by 28 by 28. So what should be the value of input channel and output channel, corner size, stride, and padding for this convolution layer to produce this desired output size? Can you guess the answer? Okay. The input channel would be the same as the channel, right? So this should be 3, and this should be 1, right? Because there's one channel. And corner size would be 5. I think I should copy. Yeah. Go Namho. Thanks for the answer. Yeah. The answer would be like this. So let's check the output size. Oh, what? Okay. Yeah. Thank you. And here's another example. This example, we saw this example during the lecture, given an input shape of 3 by 32 by 32. What will be the output shape after passing through this following convolution layer? Yeah. I'll give you 1 minute to think about it and try to fill these on your own. Okay. Yeah. Since there's a padding size of 2, this keeps the input size the same, 32 by 32. But we increase the channel, right? So we also increase the output channel to 10. So output will have 10 feature maps. Actually, these two examples are from the lecture. like this, and yeah, this. I hope you can remind this example. Okay, good. Where is the 30? Okay. The next part is batch norm and drawable layer. They also can be applied in PyTorch using torch.nn.batchnorm2d or torch.nn.drawable2d. What is the role of batch normalization? Yeah, these layer normalize the activation for each channel, ensuring that they have zero mean and univariance. And what about the dropout? Dropout randomly set some elements to zero during training, which prevents the network from becoming too reliant on any particular neuron. So it can help reduce overfitting, right? So please fill this missing value question mark in the following code. Yeah, the answer would be 3, right? Can you explain why it should be the 3 or number of features? The other value will raise errors, right? It should be 3. Yeah, the value of number feature, this argument, must match the number of input channel of X. This is because batch normalization operates independently on each channel. Oh, the channel numbers stay the same. Oh, okay. Thank you. And by C, by H, by W. Yeah. Okay. This is because batch normalization operates independently on each channel. So it should be the number of feature of the input for batch normalization to the layer. Okay. The important thing is batch normalization and drawable does not change the shape of input tensor. They operate on each element within the tensor, but yeah, do not modify the dimensions. So the shape of tensor after applying both layer, B and X or drawable B and X, remains the same size, same input size, right? We can see the print. Okay. Yeah, to understand the effect of batch normalization, we can visualize how it adjusted the distribution of pixel values. Yeah, after applying batch normalization, we can observe that the distribution became centered around 0 and with a standard deviation close to 1, which is the intended effect of batch normalization, right? This is the before, and this is the after applying batch normalization, okay? Actually, this code block isn't part of your code yet, but we are going to understand how max pool and average pool work in CNN. But I'm introducing now because we will use it. We will use max pool or average pooling later in this session. This example is related to this slide. Why is the plot before and after being same. No, it's not same. The standard deviation is about 100. The scale is different. Can you see the scale, Changmin? Okay, good. I hope you can remind max pool. For example, there's a small tensor in this slide. After max pool with 2x2 filters and stride 2, the result would be 6834, right? From the top left corner, 6 is the maximum value, right? So 6, and in this field, 8 is the maximum value. So the output would be 8. Yeah, we can just implement this simple example. Okay. I just made a simple tensor 1 1 1 1 2 2 2 2 3 3 3 3 4 4 4. And then I just reshape the input tensor to batch, channel, and spatial dimension. As you can see, after max pooling layer, max pooling selects the maximum value in each 2x2 region. So from the top left corner, 2 would be selected, and for bottom right corner, 4 would be selected, right? So the result would be like this. And also we can just apply average pool. Just change max pool to D to average pool to D. The answer would be expected. Okay. It's quite inconvenient. How can I fix this? Okay. Yeah, so now we are ready to build a simple convolutional neural network. Let's now build a simple CNN by combining a convolution layer, batch normalization, activation functions, and fully connected layer. There's some question mark. Please implement it on your own. I'll give you 5 minutes to try it on your own. After 5 minutes, let's check together. Yeah, until 54. Let's start. If you have any question, feel free to ask. Okay, time's up. Let's check the answer. For the first layer, layer 1, the answer would be 1 on our size. It would be 7. Yeah, this 1 is due to the input image channel, and 32 is for output channels, and corner size is 7. And let's try this one. So answer would be this. What about the batch norm 2D? We will apply batch normalization to the 32 channels, right? After the passing the conv 2D, the output would be output would have 32 channels, so the answer should be 32. And what about the second layer? Okay. Oh, thank you, Namu. 132. Yeah, good. Thank you. I don't know how to fix this chat. Okay. For the second layer, it would be, let's just copy 32, 64, and this would be 64. Right? And the important thing is, what would be the answer for fully connected layer here? Can you guess what it is? Since we use corner size as 7 and stride for a stride 1, it would reduce. For MNIST image, MNIST has 28 by 28 image. So when we pass this first layer, the output would be the 22. And after passing the second layer, the output would be the 16 by 16. So this should be channel multiply. Yeah, this would be the answer. 60. Yeah. Namu, can you understand what I'm saying? Yeah, since we use corner size as 7 and stride as 1, yeah, for each layer it reduces 6 by 6 dimension. Okay, so oh, good. Okay. Now we are ready to train our simple CNN model. So please just run this code. Okay. While it is running, let's explain the some line. First, please ensure that your model can run on a GPU if available. And yeah, we will use stochastic gradient descent algorithm, SGD, for optimizer. And we use cross-entry rows because this is a classification task. It is a just common option for training rows. Okay, let's wait. So far, do you have any questions? Yeah, feel free to ask because this practice session is really important for project 1. You should understand CNN well, then you can finish your project? I did not really understand where does not the number 6064. Okay. Oh, um, I hope. Okay. Let me explain. Can you remember this example? What is the input image size of the CNN? In this case, we're gonna MNIST, so the input size would be the 28 by 28. Bef yeah. Before I answer the for Seungyu, let me explain why the input of F fully connected layer is 16 by 16 by 64. As you can see, if the input size is just ignore the channel, okay? Input size is 32 by 32. When we apply a 5 by 5 filter, we can get the 28 by 28, right? Because the filter size is 5 and stride is 1, just 32 minus 5 plus 1. So in this case, the corner size is 7 and stride 1. So it would reduce the 20 after the first layer, 28 would be the 22. And after passing the second layer, 22 to 16, right? So the output of the two layer would be 16 by 16. So here 16 by 16, and also the output channel is the 64, right? So we should flatten the output and feed it into a fully connected layer that outputs 10 classes. Okay, so the answer is this. Okay, I hope this makes sense. Okay, good. And Seungyu, I have seen a code line to device to move. So far, what kind of variables do you? Yeah, it is really convention. It is really convention. If you want to train your model on GPU, you should move network to CUDA or GPU. But you can change the variable name, of course, but it is really convention. You should know this line and you should familiar with this line, okay? Good. Oh, I hope Seungyu can understand. What kind of variables? Yeah, all tensors for model, like input tensor, input image, or target labels. All the variables should move to GPU when you want to train your model on GPU, okay? Let's move on. Yeah, okay. Training is done. So after training, we can evaluate the performance of the CNN on the test set like this. Because there's a 10 classes, when we argmax the output, it would be the prediction, right? So let's check the accuracy for prediction. It would be the yeah, you should achieve an accuracy of around 99 on the MNIST test set. 99 is amazing, right? This simple CNN model works really well for a data set like MNIST. Because this is MNIST, MNIST is so easy and so common data set, we cannot achieve like this. But in reality, yeah, it is it can be happen easily, right? Is the upcoming project one at the level of today's practice? I'm not sure I can mention the level of the project, but yeah. If you understand this session well, yeah, you can handle. Yeah, don't worry. Okay, let's move on. Residual network, okay. In this section, we will implement residual neural network and see the effectiveness of residual connection in terms of test performance. Okay. Yeah, the overall structure of ResNet is like below. The first layer would be some convolutional layer and some residual blocks. Some block change the channel, and some block increase the channel 16 to 32 or 32 to 64. And at last, there's some global average pooling and fully connecting layer. I can show you a figure. Yeah. Now this is a ResNet, right? I just screenshot from the lecture. So the residual block is the fundamental building block of ResNet, right? So it consists of two convolutional layers, each followed by batch normalization and a ReLU activation function. The key innovation of ResNet is residual connection, right? Which adds the input of the block directly to the output. This is the key part of residual network. So the residual block class takes several key arguments like input channel, output channel, stride, and downsample. I think input channel, output channel, stride is really intuitive because we've already discussed about this. But why do we need to downsample? Why? Can you guess why? Why there is a downsample argument? If you know that, you're really, yeah, fully understand about residual network. Okay. Yeah, why do we need to downsample argument? This is because in ResNet, some residual blocks double the number of output channels, like this, double the output channels from 16 to 32 or 32 to 64. In this case, the stride argument is set to 2 to downsample the feature maps, which reduces the spatial dimensions since the stride is 2, while increasing the number of channels. I hope you can remember this important part. Yeah. For ResNet architecture, double number of filters and downsample spatially using stride 2. Yeah. But as the convolution can change the input size. For example, let's see here. As the convolution can change the input size if the stride is 2, right? While the short connection still holds the original size, but I mean the shortcut X doesn't change size, but output would be changed, right? So we should downsample X to match the size for output. So yeah, residual block needs to support downsampling in the shortcut path as well. I hope you can understand. Okay, downsample reduces the size of feature maps allowing the network, right? Yeah, Namo, you're right. Downsample the spatial dimension and increase the channel dimension can allow the network to focus on higher level features. You're right. So yeah, I'll give you 5 minutes to implement your own version of residual block. Yeah, after 5 minutes, let's check together. Let's start. Okay, let's check the answer. Oh, okay, let's. Yeah, I'll just copy and paste. Yeah, as you know. Okay. Okay. For the first convolution layer, the first part of the block performs convolution, Batch normalization, and ReLU. Okay. So the answer would be the 3 and how can I say? Yeah, the residual neural network use just 3x3 filter, right? So the corner size would be 3. Okay. And what about stride? Yeah. The second convolutional neural network doesn't change the shape, so stride would be 1. And yeah. Yeah, I hope this makes sense. And what about the forward function? Since the input is added directly to the output of second batch normalization layer, so we should downsample here for match the size, right? And this is the residual connection part. Yeah, I hope you can understand this part. Yeah, in some cases, we need to reduce the spatial dimensions by applying max pooling and zero padding to the shortcut, ensuring that the input dimensions match the output from the convolution layer, output and X, right? In here, downsample is just max pool to D. Okay. There's no question. Okay, the next part is ResNet class. Okay. Now let's implement the complete ResNet model. We will use a residual block we defined earlier to build stacks of residual layers, followed by a global average pooling and fully connected output layer for classification. Yeah, this part is for building this block, right? At the beginning, there's some convolution layer, and we built these blocks, residual blocks, and the finer there's a fully connected layer and global average pooling at the end, right? So please implement this code for your own. I'll give you 5 minutes to implement your own version of ResNet. Yeah, after 5 minutes, we can check. Do you need more time? If you don't, just start. The first layer of the network is 3x3 convolution that takes the input image with 3 channels and output 16 feature maps, right? So the answer would be 3, 16. What's the corner size? 3. Short one. Okay. What would be the answer of Batstorm 2D argument? It would be 16, right? After passing convolution layer, we should pass the batch normalization layer. And what about the layers 2n, layers 4, and layers 6n? This is the ResNet uses 3 sets of residual block, this. The first residual block keeps the spatial dimensions the same. So stride would be 1, right? And layers 4 and layers 6 and the second and third sets apply downsampling with stride 2, right? So it should be 2. And what about the input and output channel? Let's see the get layers. Get layers take input channel and output channel. So it should 16. Answer. Right. Sorry, 2. Oh, wait a minute. Okay. Oh, I just copy and paste. Okay. Oh, 16, 16. The output feature map is 16. So yeah, this output channel should be 16. Right? Also 3. Oops. Okay. What do you mean? Also 3? Yeah, do you have any question? Feel free to ask. Okay. Okay. Uh-huh. Good. Good. And can you intuitively understand why they should be 8 and why they should be 64? Yeah, we can calculate right away because for global average pooling, there's after 2 downsampling blocks, each downsampling block reduces the spatial dimensions by half. So the input size will reduce from 32 by 32 to 8 by 8 since there's 2 downsampling blocks, right? So the size before pooling layer here would be the 8 by 8, right? Because we're gonna train the model using Cipher 10. Cipher 10 have image with a size of 32 by 32. And here there's a downsampling block. There's 2 downsampling block. So the output would be from 32 to 32 to 8 by 8. So the size of before the pooling layer is 8 by 8. So yeah, so here, yeah, the argument would be 8. And what about 64? Let's see how FC out work. FC out fully connected layer. Once the global average pooling reduces the feature maps to 1 by 1. Yeah, because the corner size is 8 by 8, so the output would be 1 by 1, right? So since the global average pooling is applied to this tensor, yeah, here X size is 1 by 1, so the number of channel will be the final consideration. So in this case, the number of channel will be 64, right? So the answer is 64. Okay, good. So yeah, so if stride equals 2, downsample is true. Otherwise, downsample is first, right? And yeah, just build a block using the nn dot module list. It's all. Okay. Oh. Yeah, just implement all the code. Yeah, okay. Now that we have our ResNet class, we can create specific ResNet models like ResNet 18 or ResNet 32 by specifying the number of residual layers. These ResNet have argument of number of layers, right? And okay. And we can also compare the effectiveness of residual connections by creating a plain CNN without residual connection. This is a ResNet, and this is a CNN. CNN is consist of plain block, not without a residual connection. It is quite intuitive, so let's skip this block, okay? Okay, so training the ResNet model might take some time. So when you guys run this code, you can get some plot here, but I show it like right away because since it took some time. Oh, actually here. Yeah, training the ResNet might take some time, but when you look at the learning curve layer later on, you will observe the ResNet tends to learn better and faster compared to plain CNN. Yeah, this is due to the residual connections, which allow deeper neural network to train more effectively. Yeah, we just compare the ResNet and just plain CNN without residual connection. So if you use residual connection, you can make model deeper and train the model faster and more effective, okay? This is the residual network. Corb is too slow, right? Yeah, I hope you guys can understand residual neural network and implement this by your own, on your own. Okay, I think we don't need to wait until the Rose curve is out, okay? Just you will see this figure. Okay, that's all for today's session. Do you have any questions? Can you show? Ah, yeah. We're gonna upload solution to KLMS, don't worry. Can you show me again get layer function? Okay, get layer function. Let's see. Get layer. Get layer function. Yeah, this function constructs the residual blocks dynamically based on the number of layers and the stride, right? Is it so fast? Okay. Yeah, that's all. Thank you for attending today's practice session. If you have any questions, yeah, you can ask me now. And if not, yeah, bye-bye.